Good morning and welcome to Engineering Tomorrow's Semiconductor Special Lab event. We're so happy to have you guys here with us today. I hope you're ready to do some circuit work, right? We have a fantastic keynote speaker that you'll hear from a little bit later, but first, I want to hand this off to an incredible engineer that we have to lead the day, Mr. Eric Einset.
All right, thank you very much, Jillian, and I'm looking forward to the day here. It's this is a brand new lab, and there's a couple of things that are really interesting about semiconductors. There's two reasons why we developed this lab. First of all, semiconductors are a big deal these days. You may have heard about CHIPS, the CHIPS Act. Uh, we're really trying to get more semiconductor manufacturing back into the US these days. And right now, the supply chain for making chips is really global. A lot of them are made in Taiwan and around the world. So that's one of the reasons, because you guys are kind of the future workers in the US, and we want you to be aware and familiar with what semiconductors are and how they're made and how engineers are part of making them. And the other reason we did this lab is because it is such cool technology. You probably think about engineers as building big things, cars, trucks, airplanes, wind turbines, wind farms, buildings, big things, bridges. But this is where engineers are also working, and they're building tiny, tiny, tiny things. And we'll talk about how small the scale is of what these semiconductor and chips are. And the fact is they are actually everywhere in our lives. I mean, if it wasn't for semiconductors, you wouldn't have a smartphone. You wouldn't be doing TikTok. You wouldn't be, your cars probably wouldn't run. They're just everywhere. So what we want to do is show you how engineers are part of, semiconductors and all the technology. And you're going to hopefully have a fun time doing some experiments, doing some actually plating, and then you're going to hear from an engineer, a young engineer who works in the industry, and in fact, she used to work for Engineering Tomorrow, so it's really kind of fun to see that she's now gone through the whole process of becoming an engineer and is now part of semiconductor industry. So let's get started on what this is all about. Hopefully you can see my screen, or probably not. I don't think I've shared anything yet, have I? Let's start. All right. Are we clear? Can you see?
It's perfect.
Okay, excellent. Okay. So, as you know, we develop these labs, for you students, to get you familiar with what engineers do. And the labs are all developed by engineers, and also we deliver the labs. So Grace and I worked on this last summer. And just a quick background of me: I'm a chemical engineer. I actually just finished my professional career, so now I'm spending most of my time with Engineering Tomorrow. But I worked for GE and a company called Global Infrastructure Partners. But when I was in graduate school in chemical engineering, my research and what I was studying was actually a process that was involved in chip manufacturing, semiconductor manufacturing. And it was a chemical process, and you'll see a little bit later, these are chemical processes, some of them that we use to make semiconductors. So that's why chemical engineers actually do fit well with the industry. But you'll also see that electrical engineers are a big part of the chip industry, as well as a whole other bunch of different engineering fields. But it's not only engineers, but we'll talk a little bit more about other things, that other careers and other training that you can do to get into the field. So let's start with talking about what are these chips. And we're going to talk about them and use kind of the same term in many different ways. I'll say semiconductors, I'll say chips, and I'll also say integrated circuits, or ICs. So you've probably seen pictures of electronics. And they may look like what you see here on the left-hand side of the page. And quite often you'll see something that is just a black box, literally a black box. And that is an integrated circuit. So you may wonder, what is that? I mean, there's obviously a lot of things connecting to it, a lot of wires connecting into it. But what is inside that thing? And that's what we're going to talk about. That's the semiconductor, the really microelectronics that are a part of this whole industry. And these integrated circuits or chips or semiconductors, they're in your cars, they're in your refrigerators, they're in your phones, they're in your computers, they're in the monitors, they're the things that make everything work. They're in essentially in what are called data centers, which are vast buildings of computers and computing power, which is what you may refer to as the cloud. So when you're going and you're actually connecting with the internet, you're essentially in the cloud, which is essentially in a data center, and all the information that you're doing, whether it's Google, Snapchat, Instagram, TikTok, or even using AI, these are all programs that are running on these semiconductor integrated circuits. So really, you can think of the integrated circuit as the brains of the internet. It's the brains of all the data that we manage. And that's why they're so important. That's why so many countries, including the US, is so focused on making sure that we have the technology and maintain the ability to make these very, very important things. So let's open up that black box and see what's inside it. So here's a blown up picture of an example of an integrated circuit. And now first I want to point out the scale here. So this may look like a big square with a lot of stuff in it, but it's only 2.2 millimeters in dimension. So just think about how big 2.2 millimeters is. It's tiny. And if you then drill in even more in that white box, I've drilled in and you can start to see some structures in there. And what these are things like wires and little devices. And it's very, very complicated technology. And it's been developed over probably more than 50 years. And it's been developed and has, as I said, has been what has brought us into the internet age and the information age. And they basically are a part of everything that we do. So just to give you a sense of the scale here, a human hair is about 1/10 of a millimeter in diameter or thick. And so that's, if you want to think about, dimensions here, we talk about a meter, right? A meter is like a yard, roughly a yard. A centimeter is about that big. A millimeter is 1/10 of that. Okay, so now let's take a millimeter and go 1,000 times smaller, and now we talk about a micrometer, sometimes called a micron. So the human hair is about 100 microns in diameter, and you can see that how big that is on that. Sorry, on the right-hand side here, how that compares to these dimensions. So we're talking about the scale of little features that are sub-microns, even smaller than microns. And we're going to show you in a minute here, how small it can even get, what they're doing. So what are some of the things that are inside that integrated circuit? Well, a lot of the processing of code, the processing of information is done with a device called a transistor. So a transistor is essentially just an electronic device made out of a very specific type of material called a semiconductor. So it's a semiconductor material has interesting electrical properties, and that's really what has enabled all of this stuff. It's the engineering of the material properties of the semiconductors that has created this whole industry and all this technology. So you can actually buy transistors that look like this. They're basically 3 terminals, and you can hold them in your hand, and they're small and everything. But these transistors can also be made on an incredibly small scale. And here, what you have is a micrograph of a type of transistor. That's called a field effect transistor. And don't worry about understanding everything here. As you can see, there are a lot of different things. There's silicon here. There's silicon nitrites. There's some cobalt. So there's some metallic materials. And this is actually a device. And I want you to, again, look at the scale of here. Remember, we were talking about human hair is 1/10 of a millimeter, about 100 microns. If you take a micron and divide it by 1,000, you get to a nanometer. And now we're talking nanometer scales here. So these are tiny, tiny, tiny devices. And you can pack a lot of them into, one of those integrated circuits. If you zoom in on this little yellow box, you're actually seeing a structure here, and you're starting to see individual atoms of silicon. That's how small these things are. So what has happened over time is that as they've figured out how to make these integrated circuits, these semiconductors, these chips, they've wanted to make them more and more and more powerful. So they've tried to reduce the scale of the size of everything that they've been making here. And like I said in the beginning, engineers work on bridges and buildings and wind turbines, and they also work on the smallest thing you can imagine, managing and moving atoms around to make them useful for our world. So let's get the ability to make these devices smaller and smaller and smaller is actually something that Gordon Moore, who was one of the early pioneers and I think a founder of Intel Corporation, you might have heard of Intel in your computer. He noticed that as the technology for these semiconductors was improving over time, the devices were getting smaller and smaller and cheaper and cheaper. And he kind of said, this looks like it's a trend. And this is a trend that's now called Moore's Law. And basically, it's an observation that the number of transistors that you can get onto a microchip roughly doubles every 2 years, while the cost is cut in half. And if you look back to 1970, which was the early days of this, and you look at the number of transistors, on a device or in an integrated circuit, and you plot over time, so this is what, 30, 40, 50 years of development, this Moore's law just keeps marching along. Now, it's not a physical law like the gravity or Newton's laws of physics, but it's basically an observation that this technology development continues to get more and more, no pun intended with more, but more and more advanced and actually really develops. So it's an interesting thing, and the question is, will we continue on that path and get smaller and smaller? Because as we get to the individual atoms now, it's getting harder and harder technically to improve. So let's talk about how do you actually fabricate or make an integrated circuit. So it's looks really simple from this picture. You take sand, which is silica, you turn that into silicon, so the element silicon. You make a wafer, and then you cut it up into chips, and you're done. So it sounds really, really easy, but it's far, far more complicated than that. It's a multi-step process. So let's talk about some of the various steps. First of all, how do you make silicon that's ultra pure that you can start building your circuits on? And the way they do that is by a process called Czochralski growth. And that's Czochralski, in case you're wondering, this is how it's spelled. Starts with a CZ. And essentially what you do is you have a molten bath of basically liquid silicon that you've purified. And it's very high temperature. It's like 1400 Celsius or higher. You take a single crystal of silicon and you put it on the end of a rod and you put it in, and then very slowly you rotate it and start pulling out the crystal. And what you end up with is, I mean, when I say slowly, we're talking, weeks of time to actually do this. And what you end up with is this big, essentially an ingot, which is a single crystal of silicon, which now you can start to process. And what they'll do is they'll machine it, and then they'll slice that with a diamond saw into very thin wafers. And that's the starting point of making a chip. So then the next step is actually a bunch of steps. So now you started with a single piece of silicon, and now you have to start building up these little features, all the tiny, tiny wires, all the tiny, tiny transistors, all the little devices that are on there. So it's a series of steps, and it's very high technology. You have to because the scale of things are so small. You have to be extremely clean. You can't have a piece of dust. I mean, you'll see that a lot of this is all done in clean rooms. You'll see a little bit later what that looks like. You have to cover yourself so that skin from your body is getting into the process. And there are various steps. So there's oxidation, where you create an oxidation layer. There's photolithography, where you actually mask what you're trying to make. The way that you'll hear more about that, and this is kind of what you're going to be doing in a way. And then you etch away what you haven't masked. You implant different materials. You deposit metals. You polish. You dice it. You attach it to dies. There's all kinds of steps, and there's high technology in all of these steps. So it's very important, as I said, that it's very clean. And what you'll typically do is make a bunch of IC integrated circuits on a single wafer, and you want to have high yield because all you need is one thing to be wrong, one little defect, and that integrated circuit's not going to work. So yield is really, really important here. So just to talk about a couple of the specific steps that you're going to have a little exposure to. One is called photolithography. And essentially what you're trying to do is make these patterns and build these materials up. So what you'll do is you'll take a mask, which is essentially a picture of what you want to be printed on your wafer. And you'll expose some UV radiation through it. And then that will expose certain parts of your photoresist, which is another layer that's on the material, and then that can be washed off or etched away. And what will then happen is that you will create kind of a structure in your device. And you'll hear more about this because our special speaker today, Olivia, will talk more. And she's been working in photolithography and is far more experienced and knows what the current state of the art is than I do. So I'm looking forward to hearing how that's all done. I mentioned the etching then. So after you've exposed certain parts of your wafer, you then have to etch away those parts that you want removed. So what they'll do then is they'll have an etching process and they'll remove something, or maybe they'll deposit certain things. And then another thing that they'll do is they'll deposit metal. They'll have metal deposition because metal is typically what is used for conducting the electricity in a lot of these devices. So these are very complicated processing steps, and engineers are involved all over the process in trying to make sure that the yield is high and the process works well, and you get what you need out of the process. So as we've gotten further and further up Moore's law, further and further, smaller and smaller devices, these chips may need 500 plus processing steps to work. And if you don't, as I mentioned, if you don't have a good yield at each step, you're going to end up with no good devices, and that's no good. So again, it's a very, very complicated and high-tech industry and manufacturing process. So that some of the newest chips have dimensions that are on the order of 3 nanometers. And remember, we were talking a meter. 1/100th of a thousandth of a meter is a millimeter, or sorry, that'd be 100. A micrometer would be 10 to the minus 6 meters. Nanometers, 10 to the minus 9 meters. It's just getting smaller and smaller and smaller, and that's kind of the example of the state of the art here. So think about in 3 nanometers, how many copper atoms could we want to kind of engineer in there if a copper atom is only 0.2 nanometers in diameter? I mean, we're talking working with individual atoms here. And then at some of the challenges that the industry is working on to try to improve and continue on Moore's law is improving lithography, because the wavelength of light is actually bigger than some of these devices. It's unbelievable how small they are. When these chips are running, they can generate a lot of heat. And so they have to also design how the heat is going to be removed. And when the wires, these tiny, tiny wires are close to each other, they can interfere with each other electrically and just electromagnetics. So they could cross-talk. So there's a lot of design that goes in. So a lot of electrical engineering is about designing what these chips are going to look like and what devices are going to be in there. So there's always been challenges in the past, and they've always overcome them. So presumably, they'll continue to improve. So in the semiconductor industry, there are a lot of career opportunities all over the country. And the key is to find them and to get trained. And if this interests you, we'll talk about, there's a lot of things that you can do. So the various roles in the semiconductor industry, there's operators and assemblers, technicians, and then if you want to go to more advanced 4-year engineering, you can do software engineering, electrical, mechanical, chemical, and there's a lot of different options here. I actually was just last month looked up and I Googled, semiconductor programs around the country, and they have specific around semiconductors. And this isn't an exhaustive list, but you'll see that if you want to do, a full engineering degree, there are a lot of universities that have special programs in semiconductors. If you want to do more of a tech school, there are a lot of options here in New York, Arizona, Ohio, Northwest, all over Texas, all over the country, that have opportunities. So if this is interesting to you, just search your local area, and I assure you, you'll find programs that are available. And you should be interested in this because there's expected to be a lot of new jobs in the semiconductor industry. In fact, they expect about 1 million new skilled jobs by 2030. So it's a great opportunity, and the industry is looking for their next generation of workforce, which could be you. So I've talked enough about semiconductors. Let's talk about what you guys are going to do now. And you're not going to make a semiconductor, but you're going to do a couple of the processes that are kind of what they do in semiconductors. You're going to actually do a metal coating. You're going to do a metal electroplating, copper electroplating, onto a metal substrate. And but before you do that, you're going to mask the substrate. So you're going to mask the metal, and you're going to make a pattern. Then you're going to actually do the deposition. So just as an example, this is what I did. I'll show you how I did this in the next couple of slides. What I did was I took a nickel, which is not made of nickel, by the way. It's just a coin, as you know, a 5-cent piece. And I masked, I actually put a little E in here, E for engineer. I masked that with a Sharpie. And I also took a little glue and I masked Thomas Jefferson's chin here. And then I did an electroplating bath. And you can see this copper looking thing is actually copper deposition on the metal coin. And let's talk about how you do that. But before we do, there's one thing that we have to talk about. And so I want to make sure everybody's listening here, the teachers especially. We're going to be working with a material, copper sulfate, which is actually a toxic material. It is a poisonous material, and it should be treated with care. You should be treating it as if you're in a chemistry lab, and protecting yourself with what you need. So here's the bottle I have of copper sulfate. I'm just going to read the warning to be very clear. Harmful if swallowed, causes skin irritation, causes serious eye irritation, very toxic to aquatic life with long-lasting effects. So be very careful as you do this lab. This is serious stuff. So we should have provided, or you should have provided with you, safety glasses, which I'm going to put on right now. And you should also have provided with you gloves. So you don't want to get the material on your hands. It's a blue powder as a start, and it looks really nice, but absolutely treat it with care. It is poison. Okay, and then not only as you handle it, but also we'll talk about the disposal of it. We have to be very careful with it. So when you complete, after you complete the lab, wash your hands. Doing the lab, make sure you're wearing your gloves and your eye protection, and don't don't get the powder or the bath on your material, on your hands, sorry, on your skin. So this is what you're going to do. This is how you actually do the plating. So first of all, you'll start with a little cup, plastic cup. You could have this size. You might have a smaller size. That's okay. For a size this big, fill it maybe 2/3 full, or fill the cup about 2/3 full with water. And then put, if it's a small cup, maybe a little less than a teaspoon. If it's a larger cup, maybe a little more than a teaspoon of copper sulfide in the water, and let it dissolve. Then what you need to do is take your substrate. Now I showed you I used a nickel. You could use a dime. You could use a quarter. I also used a little, just a piece of metal here. Maybe you just came with a piece of metal. The most important thing is that it conducts electricity. And what you want to do is you want to clean that object with an alcohol wipe, which you should have also received in your kits. And that's just to get any oils or anything from your body from handling it, any fingerprints off of it. So you want to wash it with a little alcohol wipe, and then don't touch it anymore with your fingers. Now, as you can see, I'm holding it with a little wire. That's one way to do it. And what we're going to do is we're actually going to make a little electrical circuit here. But so after you've cleaned the coin off, I want you to take a Sharpie, which hopefully you should have received, and then you can do your artistic art on the coin or on your metal piece. Then you can make a letter, you can color in part of a pattern, you can write your name, whatever you want to do. And what's going to happen is that whatever you colored in with the Sharpie, there will be no deposition, no copper depositing there. So you're masking now that substrate from the copper deposition. So then, after you've done that, then you'll set up your little circuit, and it's a very simple circuit. You'll have one end of the material. Let's see, the coin. Let's see, connected to the coin. So the negative side of your battery, which you should have received, should go to your substrate, and then on the other end, you're going to have a piece of copper, essentially just a piece of copper. Now, in this case, in the picture, I have a little elbow from plumbing. You may have received some copper wire, and that works fine too. So just copper wire. And what you're going to do is hook that to the copper to the positive end of your battery. And then what you'll do is you'll put those two pieces, the copper and then your substrate, into your plating bath, as you can see here. You don't want them to touch. What's happening is that you're creating an electrical circuit, and some of the copper from the copper side is going to go through the water and deposit onto your substrate. So you can see how I'm doing it right here. I should have had gloves on, so that's a bad move up by me. You should be wearing gloves, and again, try not to get any of this bath material on your skin. Now, you should be able to hold it, and after a couple of minutes, you should be able to see that some copper is being deposited on your substrate, on your coin. Now, you could also deposit copper onto a penny, but it won't be very interesting because you won't even notice it. The penny already is a copper-colored looking thing. So that's why I suggest maybe a dime, a nickel, or a quarter, or just a piece of silver metal. So here, again, some of my examples. After you plate, then you want to take the coin or take your substrate out, wash it off carefully with some clean water, and dry it. And then what you can do is you take your alcohol wipe again, and you should be able to wipe away the Sharpie marks that you made on your substrate. And as you can see, I did that here. Be careful, because if you're too rough, you might rub away some of the copper itself. But basically what you've done is you've masked the substrate, and you've created a pattern. just like they do in semiconductor manufacturing. And you've put a copper layer on the rest of the substrate. Now, I'm not very good at this. I found this online. A lot of there are people who are very skilled at this and very artistic. This is a person who basically did some fancy masking, did some copper plating, and then they also actually did some plating with zinc on top of the copper, and then they alloyed the zinc and the copper to make brass. And as you can see, made a really pretty looking coin here with brass here, copper everywhere else, and this is still the bare substrate. So this is a very simple process, but it has to be controlled. So it's really important that you keep things clean, you keep your substrate clean. It's best if there's a little roughness on the substrate. If you have too much voltage, you may plate too fast and it may turn black. The concentration of copper matters. How close your copper and your substrate goes matters. So these are all factors that you can try to optimize and play with. So the question and challenge for you is, how good a plating can you make? Can you what we'd love to see at the end of the session here is we want to see what you've plated. We'd like to see the art that you've made and how it worked with masking and plating with copper. So it'll be fun just to see what you guys are able to achieve. And because it's relatively quick, you can try it multiple times if you need to, if you can't get it to work quite right the first time, and all of you students should be able to have an opportunity to do it. Now, mentioned the importance of safety here. Obviously, this is the copper sulfate is a poison and needs to be treated with care. But because it's a poison, it's also, we can't just take and throw it down the sink, because as I read, it's very toxic to aquatic life. So what I want you to do is either let this all dry out, but more importantly, whatever your normal school processes and procedures are for disposing of hazardous materials from a chemistry lab is a way you should be disposing of this. You can get the MSDS online, and whatever state regulations that you need for disposing hazardous materials should be followed. So anyway, what you're going to be doing is essentially kind of a mini semiconductor fabrication here. You're going to be cleaning your substrate. You're going to be masking it with Sharpie. You're going to be depositing material on it, and then with the copper plating, and then you're going to be etching away, basically taking a little your alcohol swab and etching away the Sharpie. So in many ways, you're doing a little mini process, semiconductor manufacturing process, very quickly. The real process of making chips can take months to do. So some of the things that you should think about, what were the important factors for getting a good plating? We'd like to hear your answers to some of these when we do the wrap up here. Is your copper plating staying attached to the coin? Could you speed up the process? And is there a problem with that? I mean, what's the quality of your plating? So these are all things to think about. So with that, I think we can hand it back, Jillian. I'll hand it back to you, and
Thank you.
you can let me see. Maybe I can stop sharing. I don't know how.
That was an awesome introduction, Eric. Thank you so much. I know you have them ready. They're ready to get to work. So let's open up those breakout rooms. You guys will work in the breakout room for an hour. We'll meet back here at 11:30 EST and for our Q&A wrap up, where you can show us what you've done, share those outcomes with us. Okay, there will be ET staff in the breakout room to assist. Let us know if you need any help, and have fun. See you soon.